In the last lesson, we learned about how we control the flight of a plane, but now we need to consider what makes a plane fly. In order to do this, we must discuss the forces acting on the plane. These forces are lift, thrust, drag, and weight. Lift and thrust are going to be the forces necessary to get us into the air, and to achieve equilibrium or cruise at the general operating conditions, all the forces must be balanced. First force is weight, or the force of gravity pulling the plane towards Earth. Weight is counteracted by lift, which is created by airflow above and below the wing. We will discuss 4 effects that impact lift, which are generalized under this one force, acting as the center of gravity for the purpose of calculating the forces acting on the plane. Thrust is produced by the power plants or engine, which is the forward acting force which opposes drag. Drag acts in the opposite direction of flight and is like friction acting between surfaces. Remember, force is a vector quantity, which means it has magnitude and direction. We discussed this in detail during POE, so this is simply a quick refresher. Remember, force vectors are represented by arrows where the length indicates magnitude and the orientation indicates direction. This image shows force 1 acting to the right with a greater magnitude than force 2 acting to the left. In this example, we have force 1 acting to the right or east with a magnitude of 75 newtons, and force 2 acting to the left or west with a magnitude of 40 newtons. Note the units of newtons for force. This is our SI unit. We'll also see pounds force, which is the customary unit. When these two forces act on the same object, the 75 newtons to the right will overpower the 40 newtons to the left, causing the object to move to the right. We call this combination of forces on the object the resultant vector, or the net force on the object. So the 75 newtons to the right minus 40 newtons to the left will give us a resultant vector of 35 newtons to the right. According to Newton's second law, net force equals mass times acceleration. So if there's a net force on the object, it must be accelerating. When considering the forces and direction of forces on an object, recall how materials can be selected to withstand those forces. So whether the object is to be acting in tension or compression, and the magnitude of that force will affect how the plane is designed. If we have equal forces acting in both directions, then the resultant vector is 0. When the resultant vector is 0, the object is acting in static equilibrium, meaning that there is no acceleration. If there is no acceleration, this means the object is at rest or is traveling at a constant velocity. So when we apply this to airplanes, if we want to move our plane from position A, assuming it's parked, to position B, we need a net force in that direction, or acceleration. Thrust will provide the force in the direction of motion. Thrust is generated by various types of engines, like propeller, turbine, ramjet, or rocket. Experiences opposition due to drag. The thrust must be greater than the drag acting against the aircraft in order for the aircraft to accelerate from rest. Drag acts in the opposite direction of flight and is only experienced when trying to move in opposition to thrust. Thrust and drag are equal or in equilibrium. The plane is moving at a constant velocity. This is steady state or general operating condition. Remember, force is mass times acceleration. We're not greatly changing our mass from moment to moment, so if we want to increase acceleration, we need to increase the net force in the direction of flight. Weight, or the downward pull of gravity, acts on our aircraft at the center of gravity. Weight is going to be the number that we're using when we're calculating lift or trying to determine the amount of lift that we need in order to counteract that weight and get our aircraft off the ground. To reduce flight, lift must counteract the weight of an aircraft. When taking off, lift must be larger than weight, but when flying at steady state, they can simply be equal to maintain the attitude of the aircraft. This is only for a short duration. As an aircraft ascends, the air becomes less dense, so lift decreases, resulting in the aircraft no longer being in equilibrium. Lift is created by the movement of air around the airfoil. The airfoil is the cross-section view of the wing. This image is of historical airfoil shapes cataloged by NACA. So you will see the progression from the Wright Flyer in 1908 to the much thicker airfoils like the NACA 747. An airfoil shape is selected for the intended purpose of the aircraft. A thinner airfoil will make for a faster plane, whereas a thicker airfoil will require a lot of thrust and be slower. Around the airfoil causes a pressure differential which produces lift. Besides the wings, other examples of airfoils on an aircraft include the propeller and horizontal stabilizer. The concept of lift is applied to other devices such as wind turbines and automobile exteriors. Lift can be increased without changing the wing or airfoil shape by decreasing the angle and increasing the speed. Created by modifying the airflow around the airfoil. We will explore 4 contributors to lift: deflection, Coanda, Bernoulli, and circulation. All lift components contribute to lift, but it's too complicated to differentiate, so they're just lumped together as total lift. Total lift is measured directly on the airfoil. The first source of lift we will consider is deflection. Deflection occurs when air molecules bounce off the airfoil at an angle from the horizontal, complementary to the angle at which the airfoil is placed, meaning they add up to 90 degrees. The air molecules will bounce off and accelerate away from the airfoil with a certain force. Due to Newton's third law, for every action there's an equal and opposite reaction. So the downward angled force of the air molecules deflecting off the airfoil will produce an upward angled force on the airfoil. This force will have horizontal and vertical component vectors. The vertical component will give the plane lift, while the horizontal component will create drag. This is called the lift-to-drag ratio. We will design the aircraft for desired conditions to optimize the efficiency of the aircraft. Note, a larger angle will increase drag and reduce lift, while a smaller angle will decrease drag and increase lift. The wing is bolted onto the aircraft at a specific angle of incidence based on the optimized conditions of the aircraft during level flight. This angle can be modified by modifying the attitude of the aircraft. Remember, that's the position or orientation of the aircraft in flight. The actual angle at which the airfoil makes contact with the air is called the angle of attack. For most aircraft, this is going to be in the range of 1 to 3 degrees. Lift we will consider is Bernoulli's principle. We may remember this from POE. Bernoulli's principle is based on the idea of conservation of energy. In a system, the energy must remain the same, so if one component of energy increases, another must decrease to maintain the same energy. Bernoulli developed this principle based on water, but air is a fluid just as water is, but with a different density. The figure shows a tube called a Venturi tube based on Bernoulli's principle. Bernoulli's principle states that as a cross-section through which a fluid travels decreases in area, the fluid velocity must increase and the pressure decrease to maintain the same flow rate. Note, this assumes that the temperature is remaining constant. When the area increases again, the fluid expands and returns to the previous pressure and velocity. When we apply this principle to flight, we look at a cross-section of air immediately around the airfoil. In order for the air to maintain the same flow, some air must go above the airfoil and some must go below the airfoil. Notice that above and below the airfoil, the air must be compressed and the cross-section reduced. However, the more camber, meaning more curved the top of the airfoil is, the more the air must be compressed. This means there is even lower pressure on the top of the airfoil than the bottom of the airfoil. This pressure differential is what gives us lift. More speed will give us a larger pressure differential and thus generate more lift. How else can we modify the amount of lift produced by our airfoil? The shape and angle of attack of our airfoil will change the cross-section and thus the amount of air compression required to maintain the same airflow. Next, we'll consider the Coanda effect. This can also be called a boundary effect or boundary layer around the airfoil. Around the airfoil, the air molecules closest to the airfoil will get a bit stuck to the surface of the airfoil, so there's a layer of air immediately surrounding the airfoil, and as the air gets further and further from the airfoil, it travels at a speed equal to the plane's velocity relative to the wing or airfoil. This air that is stuck to the wing creates a layer of fluid flow that wraps around the airfoil. This air layer pulls the wing into its flow, creating an upward force around the top of the wing. Be demonstrated if you consider water flowing from the faucet. In the first image, you see the water flowing in a free stream straight down. In the second image, the curved edge of a spoon simulates the airfoil. As the spoon dips into the water molecules curve around the edge of the spoon in the direction of the curve. This third image simply shows an overlay of where the water would land without the spoon in it. As the water curves around the edge of the spoon, the force of the water pulls the spoon further into the stream. This is something you can easily try at home. Hold the spoon loosely and feel the pull of the water as you dip it into the stream. Last, we will consider the effect of circulation. This effect will also rely on Newton's third law of motion, equal and opposite forces. The air molecules will approach the airfoil and flow above the wing. As the air comes down off the back of the airfoil, it creates a high-density area of air. The molecules try to go back up, creating a vortex of air behind the wing. Due to conservation laws, the air will flow back under the wing towards the front, creating an additional pressure gradient and generating more lift. When the four forces of flight act in equilibrium, the plane maintains steady flight. Lift and thrust must counteract drag and weight to produce flight.